Hello. Here we're supposed to find the effective spring constant of parallel springs, right? So here you can see we have two springs that are parallel to each other, and they're pulling on this block, right? So before we start this, remember that if we only have one spring, that the force that spring is equal to some constant times how far it's been stretched, right? And here's something that is new. The force is going to be to the left if you pull it to the right. So that's the opposite direction. The force will be the opposite direction of whichever way you pull it. So I'll put a negative sign, an opposite sign in front of that equation, right? Okay, so if we just have one spring, then the effective spring constant is just however much force is needed to pull it a certain distance. Usually however many newtons are needed to pull it 1 meter, right? But it's a more complicated problem to look at if two springs are acting together, which each have their own spring constant, okay? You can tell in this problem, we don't have numbers. We don't know what this spring constant is, right? And we don't know what the other spring constant is for K2, right? So we have to do what's called a formal solution, right? That means that we're going to solve it without numbers. One of the first things that we can do, we have an image, right? Let's turn that image into a diagram. Now, here's our box, right? There are two forces acting on that box, one from spring 1 and one from spring 2. Okay? They're both pulled the same distance. If you move the box to the right or to the left, both springs move the same distance, but both springs put a force on that box, right? So the effective force of those two springs is just, they're both in the same direction. It's just the sum of force of spring 1 plus force of spring 2. Whatever those numbers are, right? They could be anything. It doesn't matter. Let's leave them as variables. Okay, now putting in this equation here, force of spring 1 is equal to K, opposite of K times X. That's, if it's spring 1, it's K1. Okay, then the force effective is going to be equal to the opposite of the effective spring constant times however far it's gone. I'm actually going to move that over here. The opposite of your effective spring constant times however far you've stretched it. That equals the opposite of the spring constant for number 1 times how far number 1 has been stretched plus the opposite of the spring constant for number 2 times how far number 2 has been stretched. I see here that all terms are negative, so I'm going to turn all terms into positive because that's math. Divide by -1. And then I also see that all terms have an x in it. So I'm going to divide by x, canceling off each of those x's, right? And the equation that I'm left with is that the effective spring constant is the same as the sum of the first spring constant and the sum of the second spring constant. Here's a formal solution to the answer, to the question, what is the effective spring constant of parallel springs, right? It's simply the sum of the spring constant for the two springs. In a moment, we'll look at springs in series. So here we have two springs that are in series. Oops. You can tell that they're in series because they're connected to one another. Now, just like before, we're going to take our image and turn it into a diagram. So here, the only force acting on the box is the same as the force on spring 2, right? So in other words, the effective force is equal to the force that spring 2 puts on the box. Okay. Spring 2 puts a force on the box. The box puts a force on spring 2, right? Spring 2 is pulling spring 1 to the right, right? And spring 1 is pulling spring 2 to the left. Newton's third law, which states for every force there's an equal and opposite force, indicates that the force that spring 2 pulls on spring 1 with is equal and opposite to the force that spring 1 pulls on spring 2 with. So if spring 2 is the same as the effective force, then the force on spring 1 is the same as that, right? So here we have a beginning statement that the effective force is the same as the force on spring 2, which is the same as the force on spring 1. If you recall from before, force on a spring is the opposite of some spring constant times how far it's been stretched. So our effective spring constant is the total distance that these two springs have been stretched, which would be x1 plus x2, however far spring 1 has stretched plus however far spring 2 has stretched. And that's equal to the opposite of the spring constant for spring 2 times how far spring number 2 has been stretched. Okay. That also is equal to the opposite of spring constant number 1 times how far spring number 1 has stretched. Okay. And I'm going to write this equation opposite of K2 times X2 because the force on spring 2 is the same as the force on spring 1. That's the bottom equation here. The effective force on the series springs is the same as the force on spring 2. That's the top equation in black here. All right. Now our goal is to answer this question with a formal solution, is to write an equation for the effective for the effective spring constant here. And a good equation would only have it in terms of K1 and K2. Okay. So here I have two equations, and I'm going to want to try to get rid of these x1s and x2s, right? Okay, so what I'm going to do is I see that I have a distance that the first one has stretched and a distance that the second spring has stretched. Here I have another equation. So what I'm going to do is I'm going to solve for x1, and then I'm going to substitute that in over here, okay? First thing, I'll just make these positive, divide by -1. x1 is equal to, I'm just going to divide by k1. So spring constant for spring 2 times however far the second spring has stretched, divided by spring constant for 1. Okay. Now I'm going to take this here, since that's the same as the distance that number 1 has stretched. I'm going to substitute that in up here, right there. Okay. When I do that, here's the equation that I get. The opposite of the effective spring constant of both times K2 x2 all over K1 plus x2. If my marker works here, there we go, plus x2. And that equals, I'm going to write the equal sign over here, you can write it either side, K2 times x2 if my marker works. Okay, there's a negative there. And again, these are negative, I'm going to divide by -1. Turn those into positive, it's easier to work with. One thing that I notice here, I notice that each term has an x2 in it. So I'm going to divide by x2, however far the second spring stretches. When I do that, I've gotten rid of x2. Earlier I substituted in for x1. So now in this equation is only the effective spring constant in terms of the other spring constants. Spring constants for 1 and spring constant for spring 2. Let's clean it up a little bit. Let's make it look nicer. But this is exactly what we're going for. Okay. I'm going to rewrite exactly what we have here. When we divide, we're left with a 1. So K2 is equal to K effective times K2 over K1 plus 1. I just want to clarify that when you did this, setting this part up right here, that's the physics, right? Then you have to go through and do some tools, and those tools are not always easy to notice for solving math. But the math might seem like the most complicated part. This is the most foundational part. Recognizing that the effective force on the spring is the same as the force on spring 2 and the same as the force on spring 1. That's the important takeaway. You'll learn the tools. Okay, so let's keep working here. All that I'm going to do is I'm going to divide by K effective, divide both sides by K effective, and I'm going to divide both sides by K2. Okay, so I'll have 1 over K effective, and that's going to equal 1 over K2 times K2 over K1 plus 1. When I distribute that 1 over K2, it's going to cancel with the K2 in the first term. And then I'll have 1 over K1 plus 1 over K2. That is equal to, and I'm just going to rewrite this just to put a box around it. That is equal to 1 over K effective. Here is our formal solution for the effective spring constant on a set of series springs. That's the same thing that we had up here. It's just written in a more legible form. Thanks. I'll be back shortly to answer questions. And keep reading your packet.